In this video, we're going to start Chapter 3 of the chemistry textbook. Chapter 3 is on mass relationships in chemical reactions. So there's two parts to this chapter. The first part is these first 6 sections, which are just about what is atomic mass and molecular mass, and how exactly do we quantify masses at the atomic level, quantify and work with them to analyze mass relationships and atom or molecule relationships in elements and compounds. Okay, the second part is these last 4 sections, and these are about mass relationships in chemical reactions. So a chemical reaction we represent with a chemical equation, to where you start with one or more compounds that are called the reactants, and these interact and undergo a chemical reaction, and what results is one or more compounds called the products. And so what are the mass relationships in a chemical reaction between reactants and products? What we're going to see is the foundation for this analysis is the law of conservation of mass. This is one of the fundamental conservation laws that applies not just in chemistry, but in all systems in science and physics. Okay? But we're going to start with, in this video, part 1 of this chapter, where we're just thinking about what exactly is atomic mass and molecular mass, and how are we going to even think about quantifying masses on the atomic level, and not just masses, but even counting the number of atoms or molecules in a substance. Okay. In this chapter, we will consider the masses of atoms and molecules and what happens to them when chemical changes occur. Our guide for this discussion will be the law of conservation of mass. So yeah, the law of conservation of mass isn't really going to come into play until part 2 in an upcoming video, where we're talking about the mass relationships in with chemical changes, chemical reactions. And so right now we're just wanting to think about the idea of atomic mass. So the mass of an atom. So if we're going to answer the question, what is the mass of an atom, then the precise answer to that would be the mass of all the protons, all the neutrons, and all the electrons. Add all of that up, and there you get the mass of the atom. And that's exactly right. That's the precise meaning of the mass of an atom. Okay, but we want to be specific and clear on exactly what we're talking about here. So we learned in the previous chapter the exact meaning of an atom, as far as, so when we look at the periodic table and look at any of the elements, remember an element and an atom are technically not the same thing, in the sense that, so if you look at the element oxygen, well, that element comprises, in most circumstances, multiple specific atoms, because there's different isotopes of oxygen. So if you're specifying a specific atom, then you need to say, okay, you have the element oxygen, and then furthermore specify the isotope, because oxygen 16, oxygen 17, and oxygen 18 are different atoms. They're the same element, meaning that they have the same number of protons in the nucleus, the same atomic number, but they're different atoms because they have different numbers of neutrons in the nucleus. They have different mass numbers. Okay? And so really with atomic mass, we're thinking about a specific type of atom, okay, and then so an isotope of a certain element, and then precisely the mass of the atom is, you take the mass of all the protons and all the neutrons and all the electrons, add those together, and that is the precise atomic mass. Okay, but now we can think about how in the previous chapter we did learn about the mass number. So you have a chemical symbol here like Fe or Au, and then here is the mass number, and here is the atomic number. And we know the mass number is an integer count that represents the total number of protons and neutrons in the nucleus. Okay, and so why is this called the mass number? Why does it have the name mass attached to it? Well, because we learned that the proton and the neutron have close to the same mass. It's not exactly the same, but they're close. It's not until the third or fourth decimal place to where you get a difference in mass between the proton and the neutron. And then the electron mass is about 2,000 times less than the proton and the neutron mass. So when you think about the total mass of an atom, a very large percentage of this mass is going to be contained with the protons and the neutrons, so just in the nucleus. And so that's why the count of protons and neutrons, you can call that the mass number. But it actually goes a little bit further than that, because you might think, well, that's just a count. That's not an actual mass. But we're going to see that the count of protons and neutrons, that just the integer count, is still very closely related to the actual numerical mass as well. We'll talk about that in a second. Okay, but right now, if we're thinking about the mass of an atom, we need to specify a specific isotope of an element, a specific atom, right? And say, okay, what is the mass of that specific atom? That atom that it has this many protons and this many neutrons in the nucleus and this many surrounding electrons. And you can think about, we could even talk about the mass of an ion. However, the change in mass going from a neutral atom to an ion, since it's just like a 1, 2, or 3 electrons leaving, it's not going to, the mass is going to be, difference is going to be very small. But still, technically, from a precise standpoint, the ions have slightly different masses than the corresponding neutral atoms, or molecules if it's like an ionic molecule. Okay. In this chapter, we will use what we have learned about chemical structure and formulas in studying the mass relationships of atoms and molecules. These relationships, in turn, will help us to explain the composition of compounds and the ways in which composition changes. The mass of an atom depends on the number of electrons, protons, and neutrons it contains. Yeah. From a precise standpoint, it's the sum total of all the electrons, protons, and neutrons. Knowledge of an atom's mass is important in laboratory work, but atoms are extremely small particles. Even the smallest speck of dust that our unaided eyes can detect contains as many as 1 times 10 to the 16th atoms. Clearly, we cannot weigh a single atom, but it is possible to determine the mass of one atom relative to another experimentally. The first step is to assign a value to the mass of one atom of a given element so that it can be used as a standard. Okay, so, yeah, we obviously can't, definitely back in the day, in that whole 1800s period when atomic theory was gaining traction and they were discovering elements, etc. But even still today, we definitely can't think about like weighing a single atom like we would a marble or something, right? Like taking a single atom and putting it on this atomic-sized scale and weighing it. Now, you never know. Maybe with like they're making nano machines right now, and with electron microscopes, as technology increases, maybe in 100 years, 200 years, we will be able to weigh single atoms. But right now, and in the 1800s, we can't do this. Okay, but what you can think about is what they were able to do at the time, and what we can do today. The way we do take mass or weight measurements of atomic-sized particles is we could determine masses of atoms or molecules or atomic-sized particles relative to other atomic-sized particles. That's the next best option that we can do. Okay, so like today, this is done with what's called mass spectrometry, which we'll discuss either at the end of this video or in a upcoming video. Okay, and so what you're doing here, these relative masses, is you're saying something like, okay, I've got a hydrogen atom, let's say the isotope with mass number 1, so 1 proton and 1 electron, no neutrons. You could maybe put in some oxygen atoms into this spectrometer and determine that, I'm just throwing numbers out here, but determine that this oxygen isotope has 8 times as much mass as this hydrogen isotope, right? You're not saying anything specific about the hydrogen isotope or the oxygen isotope, because you can't take those and like just put them by themselves on a scale, but you can make a relative statement between the two. Okay, and so that's what they're saying here in regards to the first step is to assign a value to the mass of one atom of a given element so that it can be used as a standard. Okay, it says by international agreement, atomic mass, sometimes called atomic weight, is the mass of the atom in atomic mass units. One atomic mass unit is defined as a mass exactly equal to 1/12 the mass of one carbon-12 atom. So what they do is to work with these relative masses to make it easier to specify masses at the atomic level, even if they're relative masses, is so it would be like that they would say this hydrogen isotope with mass number 1, we're going to assign this a value of 1. We're going to make up a unit, call it atomic mass units, AMU, and we're going to say we're going to define this to have a value of 1 atomic mass unit. And this is useful because then you can say, all right, well, if I'm measuring the oxygen 16 isotope and I figure out that, and again, I'm just throwing out numbers here, that it has 8 times as much mass as this, well, then since this has mass 1 AMU, that means this has mass 8 AMU. You see? And then you could kind of put this off to the side and compare the oxygen 16 isotope to like a selenium isotope. And you figure out, okay, this has 4 times as much mass as this, so this must be 32 AMU. And then you compare selenium to a silicon isotope and see that it has the silicon isotope has half as much mass as this, so its mass is 16 AMU. You see? Now, but make sure you note, though, that at this point, if we're following along here, like it's a storyline, then so they're determining these relative masses in the 1800s in AMU like this. But even though the AMU is defined, these masses are still purely relative, meaning that we don't know at this point, we have no conceptual idea of what 1 AMU is. In the same way that if we're defining units of, say, velocity, I could say, okay, I'm going to make a unit called 1 Lamborghini. That's a speed. So I can say a Camaro is 3/4 of the speed of a Lamborghini. It's 3/4 Lamborghinis. The unit is Lamborghini. A Jaguar is 1.5 times the speed of a Lamborghini. And then for, I could say the speed of a turtle in Lamborghinis, that, okay, 1,000th of a Lamborghini is the speed of a turtle, but maybe I wanted to find a different unit for slower speeds. So I say I'm assigning a unit of 1 turtle. That's another unit. And I'll say a snail is 3.5 times the speed of a turtle, 3.5 turtles. Right? But in that case, we would have a conceptual idea of these units. I could go measure the speed of a Lamborghini, take like an electronic timer. It's in seconds and also like a distance timer as well. It's in feet or meters or miles and get the speed of the Lamborghini. I can conceptualize what a speed of 1 Lamborghini is relative to units, feet and seconds that I'm familiar with. At this point, we have no conceptual idea of what an AMU is. We can't say, okay, well, look, we know what a gram is, right? We weigh things in grams. We have a conceptual idea of what a gram is, how much mass a gram is. Well, how many grams is an AMU? We have no idea, right? It's not like just having pure relative masses isn't useful, but still. Okay, so now, but it says here the unit for atomic masses by international agreement. It says here, so yeah, like atomic mass is the mass of an atom, but we're really referring to any masses on that atomic sized scale. So electrons, protons, molecules, etc. The unit we use is called the atomic mass unit, right? It's kind of like we have units of millimeter or kilograms, etc. You've got different units. We had a unit for slow speeds, the turtle, and faster speeds, the Lamborghini. Well, for masses at these small scales, it's accepted to use at the atomic size scale. We use what's called atomic mass units, AMU, and the atomic mass unit is not defined relative to the hydrogen isotope with mass number 1. It's defined to be, it's the mass that is exactly equal to 1/12 the mass of a carbon-12 atom. So there's different isotopes of carbon, but you have the isotope that has mass number 12, 6 protons and 6 neutrons in the nucleus. So that we've constrained a specific atom in that case, a specific isotope. There's only one unique type of carbon-12 atom. You take that carbon-12 atom, and if you divided it into exactly 12 equal pieces in terms of mass, then one of those pieces, the mass of one of those pieces, is defined to be an AMU. Okay, and so you can think about why the AMU is defined this way, because the building blocks of all matter, in particular in terms of mass, is the protons and the neutrons, right? All elements, all matter, if we're thinking about the masses, is all tied up with the mass numbers, right? The number of protons and neutrons. So from a mass standpoint, 1/12 the mass of a carbon-12 atom is going to be the mass of a single proton and a single neutron, since they weigh close to the same amount. So in AMU then, based on the reason why this definition is used, is because when you use this definition for an AMU, you're saying that a proton and a neutron are going to weigh very close to exactly 1 AMU. And that's perfect, right? Because that's what in terms of mass, that's the building blocks for all matter, is protons and neutrons. Okay, and that's exactly what we see. All right, here's the carbon-12 atom. You have the 6 protons, 6 neutrons, and the 6 electrons. But since like 99-point-something% of the entire mass of the carbon-12 or any atom is contained with the protons and the neutrons, then if you define the mass of this atom to be 12 AMU, then the result is the mass of a proton and the mass of a neutron are going to be nearly equal to exactly 1 AMU. Okay, now, but if we dig into this a little bit deeper, there's some confusing points that come up. All right, so if we look here, we can say, all right, let's take 6 times the mass of a proton, 6 times the mass of a neutron, 6 times the mass of an electron, add those up. It should be exactly 12 AMU by definition. But that's clearly not going to be the case. These are the proton and the neutron here weigh more than 1 AMU. So just the 6 protons and 6 neutrons is going to weigh more than 12 AMU. So what's going on? Well, what's happening is when you see just the general reported mass of a proton or a neutron, what's being reported is a proton and a neutron just on its own, by itself. Okay. However, if you're thinking about protons and neutrons in a nucleus, in which case they're called nucleons, because it's such high energy, it's an incomprehensibly dense packing of protons and neutrons, and it's all positive charge with no negative charge to neutralize it. So it's like extremely high energy. What happens is energy mass interactions start to come into play. Very slightly, but they come into play. The E is equal to mc squared factors in. Mass is converting to energies. And so because of that, if you're going to state the definition of the AMU precisely from the perspective of protons and neutrons, then really what you're saying is if you take the mass of 6 protons and 6 neutrons as nucleons, so meaning they're all contained together within a nucleus, and then you add that to the mass of 6 electrons, then that is going to be equal to exactly 12 AMU. So you have to specify if you're referring to protons and neutrons as nucleons or by themselves. Okay, now, if we dig a little deeper, there still is a little bit more confusion, because we can think about, so, okay, with with that in mind, we might be able to say something like this. We can say, okay, well then if we think about, we have a proton and a neutron as nucleons contained within the carbon-12 nucleus, and then we have this single electron surrounding the nucleus. And so if we take this as a trio here, then we could make a statement that there's 6 of these trios in the carbon-12 atom. And they're all the exact same. It's these 6 equivalent trios of a proton and a neutron as nucleons, and then a single surrounding electron. And so with 6 of these trios, if this weighs 12 AMU, then that means this must weigh exactly 2 AMU. And that's exactly correct, absolutely. This proton and neutron contained together as nucleons in the carbon-12 atom, and this single surrounding electron are going to weigh exactly 2 AMU. Okay? And so then we could think about, well, maybe we could make a statement that, so if you have the oxygen-16 isotope, okay, well, there's 8 of these trios in the oxygen-16 isotope, right? There's 8 of a proton and a neutron as nucleons, a single surrounding electron. There's 8 of those. So these weigh 2 AMU, and so that means that oxygen-16 is going to be 16 AMU. Okay, well, sometimes this kind of analysis works. I actually think the oxygen-16 isotope does weigh 16.00 AMU, but most of the time, this is not going to work. You can't analyze it this way. For example, if we look at at deuterium, the isotope of hydrogen with 1 neutron in the nucleus, mass number 2, well, okay, this has a proton and a neutron in the nucleus as nucleons, a single surrounding electron. Boom, perfect. This should be exactly 2 AMU. But it's not. It's close. It's like 2.00 something AMU. And so what's going on is you really need to think about, you can't just, you have to specify, okay, this is a proton and a neutron as nucleons, but contained within what nucleus? This proton and neutron are contained within a nucleus that has a total of 6 protons and 6 neutrons. This proton and neutron pair is contained within a nucleus that only has it has 2 protons and neutrons, right? You have to take the entire nucleus with all of its protons and neutrons as a whole. You see? Now, just to point out, though, it's not like you couldn't just make the assumption, like look at all of matter as these building blocks of protons and neutrons, and you determine all masses by making the assumption that a proton weighs 1 AMU, a neutron weighs 1 AMU, neglect the mass of the electron and determine masses that way. That you're going to get very accurate masses doing it that way. I mean, look, you don't deviate from 1 until the 3rd decimal place here. And then again, the electron is, it's not to the 4th decimal place where the electron mass comes in. So you could calculate masses from that perspective, or even, just like discuss masses from that perspective of like pretty much a count of protons and neutrons. Just use the mass numbers. However, for the sake of intuition, we're trying to analyze this from the exact precise perspective of what's going on. Again, for the sake of intuition, right? Technically, a proton and a neutron do not weigh the same amount. Okay. So it says, carbon-12 is the carbon isotope that has 6 protons and 6 neutrons. Setting the atomic mass of carbon-12 at 12 AMU provides the standard for measuring the atomic mass of the other elements. For example, experiments have shown that, on average, a hydrogen atom is only 8.4% as massive as the carbon-12 atom. Thus, if the mass of one carbon-12 atom is exactly 12 AMU, the atomic mass of hydrogen must be 0.084 times 12, or 1.008 AMU. Similar calculations show that the atomic mass of oxygen is 16.00 AMU, and that of iron is 55.85 AMU. Thus, although we do not know just how much an average iron atom's mass is, we know that it is approximately 56 times as massive as a hydrogen atom. Yeah, we know these relative masses that we report in AMU. Okay, and so now, again, I want to note here, if we had a table that showed not just the elements, but all of the isotopes of the elements as well. So like you had all three of the main isotopes of hydrogen here, and same with the rest of the elements. Okay, if each of those isotopes, you could see what their atomic masses were, kind of like what's shown here, but we haven't talked about yet what exactly these masses mean, since they're not corresponding to a specific isotope, right? But again, let's imagine that for each of the elements, they were sectioned out to where you could see the different isotopes. And then each of the isotopes had an atomic mass of that isotope in AMU. Okay, what you would see is, you would see carbon-12 would be exactly 12. And every now and then you would see something like we just saw oxygen-16 was like 16.00 AMU. But in the majority of the cases, the majority of the isotopes aren't going to be a perfect integer. Okay, so just remember that. And it's because of exactly what we just talked about. It's that binding energy in the nucleus slightly alters those masses a little bit, right? So we would see the atomic mass of hydrogen with one proton and one electron is 1.008. Iron, 55.85, right? A specific iron isotope, 55.85. So most of the time, even with specific isotopes, specific atoms, you're not going to see these integer values of atomic mass in AMU. And that's a common misconception, because people can tend to think that the main source of not having integer values for atomic mass is because of what we're about to talk about here with how you represent the elemental masses with these averaging of atomic masses. But that's actually not the case. Even with specific isotopes, you're constraining there's no averaging. You're constraining a specific atom. It's still not going to be an integer. Again, because of those energy mass interactions in the nucleus between the protons and the neutrons. Okay, so now we understand the atomic mass in relation to specific atoms, specific isotopes. But what is this? Reported for iron here, you have this atomic weight. But I mean, what isotope is this referring to? What are all of these masses shown here that are just associated with an element? But an element isn't an atom, right? It's not constraining a specific atom. So what are these values? Okay, so in general, in nature, or in just common industrial processes, in more natural circumstances, if you have an elemental form of a substance, it's like carbon, you've got graphite and diamond. Oxygen, you've got the O2 and then O3, ozone, etc. It's not like if I bought a pack of lead pencils, which is, the graphite is what they call the lead in the lead pencils. It's not like, okay, this one lead pencil I'm using has the carbon is made up of all of the carbon-12 isotopes, but then another lead pencil is going to have the carbon-13 isotopes. No, it doesn't work that way. Unless you've got some special circumstance of temperatures and pressures, or you're applying like electric currents to something and you're manipulating the substance, then in general, natural substances, elemental forms of substances, are just going to contain a mixture of all of the isotopes. Now, it's not necessarily an even mixture, like it doesn't have to be 50% carbon-12 and 50% carbon-13. No. But it's still going to contain this distribution of the different isotopes. If you have a diamond, or if you have graphite, or if any elemental form, and you're looking at it in a lab, or you're holding it in your hand, whatever, it has all of the different isotopes of that element mixed in. And the proportions in which the isotopes are mixed in, chemists determine and report. So, for example, the natural abundances of carbon-12 and carbon-13 and naturally occurring elemental carbon is going to be 98.9% carbon-12 and 1.1% carbon-13. But for other elemental forms of substances, like, for natural oxygen, what's the percentage of oxygen-16, oxygen-17, oxygen-18? Would be some other proportion. And so because of that, what's reported as the mass of an element in general, the mass of a general element, which you can think about when it comes to analyzing chemical reactions, chemical equations, processes in nature, we're going to want to use this mass because we're dealing with just natural substances, right? Okay. What's reported is the weighted average of all of the different isotopes. So with carbon, if you have 98.9% carbon-12, 1.1% carbon-13, then what's reported here is you take 0.989, the percent, times 12, and then 0.0110 times the mass of carbon-13, and you get 12.01 AMU, which is what's reported for the mass of elemental carbon. It's really close to 12 because 98.9% is carbon-12, right? If it was 50% carbon-12 and 50% carbon-13, it would be, close to 12.5, slightly higher than 12.5. Okay, and so that's what these masses are. They're called atomic weights. They're the masses of these, the elements, the naturally occurring elemental form of these substances. Okay, now a common convention is to refer to these elemental masses as atomic weight and then use the term atomic mass specifically in the case where you're talking about an actual specific atom, a specific isotope. However, you can see here that the textbook adopts the convention that you can use the term atomic mass and atomic weight interchangeably, however you want, right? They said here, atomic mass, sometimes called atomic weight. So if you want to refer to this elemental average as atomic mass, you can. Or if you want to refer to the mass of the selenium-34 isotope as atomic weight, you can. I personally like the convention of distinguishing between atomic weight and atomic mass, but it's up to you. Okay, now again, though, take note of the fact that it's very easy to, when you see these atomic masses or atomic weights and you see these non-integer values, it's easy to strictly associate the non-integer values with atomic weight, with that average elemental mass, to associate it strictly with atomic weight. And then to in the back of your mind think that, okay, but when I'm dealing with a specific isotope, then I'm going to start getting integer values, right? Like carbon-12. The carbon-12 weighs exactly 12 AMU. And then you'll see oxygen-16 weighs 16.00 AMU. So when it comes to specific isotopes, you get these integer values. You don't get these decimals like this. No. Even with isotopes, because of those energy mass interactions in the nucleus, you're still going to be getting these non-integer values most of the time. Okay, so when you look up the atomic mass of carbon in a table, such as the one on the inside front cover of this book, you will find that its value is not 12 AMU, but 12.01 AMU. The reason for the difference is that most naturally occurring elements, including carbon, have more than one isotope. This means that when we measure the atomic mass of an element, we must generally settle for the average mass of the naturally occurring mixture of isotopes. For example, the natural abundances of carbon-12 and carbon-13 are 98.9% and 1.1% respectively. The atomic mass of carbon-13 has been determined to be 13.00335 AMU. Thus, the average atomic mass of carbon can be calculated as follows with a weighted average. Okay, it is important to understand that when we say that the atomic mass of carbon is 12.01 AMU, we are referring to the average value. If carbon atoms could be examined individually, we would find either an atom of atomic mass exactly 12 AMU or one of 13.00335 AMU, but never one of 12.01 AMU. So, yeah, if you're looking at any naturally occurring elemental form of a substance, then if you separated out the isotopes, their masses are not going to be equal to the average atomic weight elemental mass, right? But again, they're also not necessarily, most of the time, going to be these perfect integer values either, except for here you're dealing with carbon-12, and that's the definition of the AMU. Okay, the atomic masses of many elements have been accurately determined to 5 or 6 significant figures. However, for our purposes, we will normally use atomic masses accurate only to 4 significant figures. For simplicity, we will omit the word average when we discuss the atomic masses of the elements. So yeah, you can see the textbook here doesn't really want to distinguish between atomic weight and atomic mass, which to me, I find that a little bit confusing, because then it's hard to tell what, are you dealing with that weighted average mass, or are you dealing with a specific atomic mass? So the way I like to do it is I like to try as best I can to say atomic. If I say atomic weight, I'm referring to that averaged elemental mass. If I say atomic mass, I'm referring to the mass of a specific atom. But, sometimes it's hard to follow that convention. So, but yeah, just try and keep this in mind. Okay. Avogadro's number and the molar mass of an element. So now we want to bridge that gap between masses and counts at the atomic scale and the macro size scale, the human size scale. So it says atomic mass units provide a relative scale for the measures of the elements. But because atoms have such small masses, no usable scale can be devised to weigh them in calibrated units of atomic mass units. Yeah, we can't calibrate a scale in AMU. To where then, like, you take an atom or a molecule and put it on the scale, and it's balanced in terms of AMU. At least not in the year 2025, we can't. Therefore, it is convenient to have a special unit to describe a very large number of atoms. The idea of a unit to denote a particular number of objects is not new. For example, the pair, 2 items, the dozen, 12 items, and the gross, 144 items, are all familiar units. Chemists measure atoms and molecules in moles. So yeah, to bridge this gap, we use this special unit called the mole. All right. The first thing to note about the mole is that it's just a number. It truly is just a number. In the same way that a pair is a number, a dozen is a number. And what I mean by that it's just a number is, so you don't need to know the history of where the dozen came from to use the word dozen, right? I don't even know where the word dozen comes from. But I could say a dozen eggs, a dozen peanuts, a dozen cars, a dozen protons, a dozen neutrons, a dozen H2O molecules, right? That means I'm saying 12 of those, what we call elementary entities, 12 of whatever we're referring to, right? It's the exact same thing with the mole. The mole just corresponds to some number. Instead of 12, it's this 6.022 times 10 to the 23rd, this big number. Okay, and you just use it to say a mole of whatever you want, whatever elementary entity you want. It's up to you. A mole of cars, a mole of eggs, a mole of protons, a mole of H2O molecules, a mole of iron atoms, right? I don't need to know the history behind where the mole came from to use it. And so if we look at this definition here of the mole, it says the amount of a substance that contains as many elementary entities, atoms, molecules, or other particles, as there are atoms in exactly 12 grams of the carbon-12 isotope. So this last part of the definition here is giving you where the mole came from. This last part is saying, so let's say this said dozen instead. Then this last part would say, as there are, it would kind of give you the history of the dozen, where it came from, and you would say, okay, that means 12. Well, this here, as there are atoms in exactly 12 grams of carbon-12, that's pointing to the Avogadro's number, the 6.022 times 10 to the 23rd. Okay, now the first part of the definition, the amount of substance, is, so whenever we use the mole, the majority, if not all of the time, it's going to be in reference to like atoms or molecules or these tiny particles within a substance. Why would we use it for any other reason, right? That's why they're saying, look, elementary entities, we're going to be in general referring to atoms, molecules, these atomic-sized particles. But they technically didn't have to constrain it like this. It really, if you're going to put the dozen, like let's say this was the dozen, the definition of the dozen, it would say the amount of elementary entities, whatever you want, cars, boats, whatever, that there are in, and give you the history, which implies 12, right? So if you have 12 of anything, you have a dozen. And they could have just said it that way here. The mole is the amount of elementary entities, whatever you want, that there are in exactly 12 grams of the carbon-12 isotope, which points to the Avogadro's number. If you have this 6.022 times 10 to the 23rd of anything, then you have a mole of that. Okay, great. Now, but what is the mole? What is this number, and how does it help us to bridge that gap between atomic-sized masses and counts and the macroscopic human world? Okay, so what we do to bridge this gap is we say that, okay, we're going to choose a specific atom. So like a fully constrained atom, a specific isotope of a certain element. Okay, we're going to choose this specific atom, and then we're going to say, okay, now let's think about that we have a certain amount of this atom as a substance. It's still just that pure single atom, but now we have a certain number of grams of this atom as a substance. And we're going to pick a certain number of grams. Okay, so we've got this specific atom as a substance, a certain number of grams of it. And what we want to do is we're going to experimentally and at the same time analytically estimate to as high of precision as possible how many of those atoms are in that sample of substance. And the number of those atoms is going to be this special number that we'll use to bridge that gap. And we'll call this number the mole. Okay, that's the strategy. Now, the question is, what type of atom do you choose? And then how many grams of that atom as a substance do you choose? Right? You could really do whatever you want, as long as it's a pretty abundant type of atom, the elemental form is pretty abundant, like, like oxygen or carbon or hydrogen, iron maybe. You could choose any like specific type of atom you want, and you can pick any amount of that substance that you want. 4 grams, 10 grams, 20 grams, 100 grams, right? So what are you going to choose here? Well, what's chosen, that the most clever way to do this is to have it line up, be parallel with the way that the AMU is defined, right? We're trying to bridge that gap between masses and counts at the atomic level. Well, let's make it parallel with atomic masses, the AMU. All right, so to do that, what you do is you say, okay, well, the atom is naturally going to be the same exact atom that we use to define AMU, carbon-12. Okay, now how many grams of carbon-12 are we going to choose? Well, let's do 12 grams, right? Because it's 12 AMU is what's defined to be the mass of carbon-12, a single carbon-12 atom. Well, okay, let's say we're saying 12 grams of the carbon-12 isotope as a substance. Let's make this what we investigate, what we're striving to experimentally determine to as accurately as possible how many of these carbon-12 atoms are in 12 grams of carbon-12. That's the number we're gonna search for, that we call the mole, or also known as Avogadro's number. Okay, and experiments and analysis show that in 12 grams of carbon-12, there are 6.0221413 times 10 to the 23rd carbon-12 atoms. And that's Avogadro's number. That's the mole. And as technology advances, they're constantly striving to make this more and more precise. Now, you might say, well, wait a minute. How could they possibly know this? How could they possibly figure this out? To, what is this, 7 decimal places? Right? I mean, atoms are incomprehensibly small, mind-blowingly small. How could we possibly determine this to this level of precision? Well, the first thing you want to note is is that it's not as precise as it looks. I mean, it's still really amazing, but it's not as precise as it looks. This is not precise to 7 decimal places because this is in scientific notation, right? This is, it's if we bring the decimal point here where the significant figures end, okay, well, we're still left with 16 trailing zeros. So it's only precise to 10 to the 16th. So really what you're saying here is in 12 grams of carbon-12, there's 6.022. You're estimating that there's 6.022 times 10 to the 23rd carbon-12 atoms plus or minus 10 to the 16 carbon-12 atoms. Right? That's why I'm saying it's really an estimate because it's plus or minus 10 to the 16th. Okay? But I mean, even then, it's still kind of mind-blowing to how could they even figure this out? Right? Well, I go into the details of the discovery and development of Avogadro's number in a separate video. But just to give you a little bit of a preview, scientists have learned a lot about matter, energies, physics, etc. through the study of gases, substances in the gas phase. Because gases are significantly easier to study than the liquid and solid phase. Significantly simpler to study. We're going to learn about gases in Chapter 5. Okay, and so like, for example, we discovered absolute zero temperature, the lowest possible temperature, 0 Kelvin, 0 Rankine, through the study of gases, in particular ideal gases, gases that are approaching ideal behavior. We talk about this in Chapter 5. It's very interesting. Okay, and for example, so this is Avogadro's number, but Avogadro's law states that if you have any ideal gases, that they could be different gases, they're made up of different molecules, different atoms, completely different gases, but if they're at the same pressure, temperature, and volume, then the number of gas molecules between all the gases must be the same, right? And so you can see how you can study gases to gain insights into just the general properties of matter. Okay, so, but now, how does the mole, Avogadro's number, allow us to bridge that gap? How do we use the mole to bridge that gap between atomic masses and counts and the macroscopic human world? Well, okay, so if you're thinking about any specific atom, a specific isotope, or even just an element, there's 2 properties that any given atom or element has. Okay, one property is the atomic mass or atomic weight of that atom or element, right? You could still even think about an element as having an atomic weight, even though we're not talking about a specific atom. You kind of think about it as all of those isotopes grouped together, right? So any atom or element, a property associated with it is its atomic mass or atomic weight, just the mass of that atom. Okay, another property of an atom or element is called its molar mass. Its molar mass. And all molar mass is, all it's saying is the units of the atomic mass of an atom or element, it's AMU, and molar mass, it's grams per mole. Okay, all the molar mass is telling you is how many grams of this atom or element do I need to where once I have this many grams, then contained within that sample is 1 mole of those atoms. How many grams do I need to where once I have that many grams, then I have within that sample, that substance, 1 mole of those atoms. 6.022 times 10 to the 23rd of those atoms. That's what the molar mass of a specific atom or an element is telling you. And again, it's kind of confusing when you think about the molar mass of an element, but you can still think about it that way. If you have the molar mass worth of grams of that element, then you've got a mole worth of those the mixture of those isotopes. in that same percentage abundance of those isotopes for that element, right? We had like the 98 point whatever percent of carbon-12, and then the remaining 1 point whatever percent was carbon-13, right? So if you have a molar mass in grams worth of carbon, then you have 6.022 times 10 to the 23rd carbon atoms, with 98% of those being carbon-12 and the other 1 point whatever percent being carbon-13. Okay, now, because of the way in which the mole is defined relative to the carbon-12 atom and 12 grams, and then since the AMU is relative to the carbon-12 atom and 12 AMU, because of this, if you look at the atomic mass of any atom or element in AMU, it's going to be some number, right? Like 15.999 or 20.180. It's going to be some number. That number, that numerical number, is going to be the molar mass of that substance as well. So like for the element neon, its atomic mass is 20.180 AMU. Well, its molar mass is going to be 20.180 grams per mole, right? So this is kind of confusing. It's not like these two are equal, because these are different properties, they have different meanings. This is AMU, this is grams per mole. It's just that the numbers are numerically equal is all, right? So what I mean is, so an atom of neon, which like on average in the element neon, an atom has a mass of 20.180 AMU, okay? But now separately, a different property is that you would need 20.180 grams of neon, to where at that point you could say, okay, within this substance here, this sample, there's a mole of neon atoms. 6.022 times 10 to the 23rd neon atoms. Okay, and so you might say, well, man, how do these match up like this? These two numbers end up being the same. It's just because of the way it's defined. Again, the mole could have been chosen to be based on some other atom and some other mass, but no, they systematically chose it to be the carbon-12 isotope and 12 grams, and that's why it works out that way. Okay, but still, though, how exactly does this allow us to fully bridge that gap between atomic sizes and human sizes? Because it still probably isn't fully clear to you. So let's keep reading. The actual number of atoms in 12 grams of carbon-12 is determined experimentally. This number is called Avogadro's number in honor of the Italian scientist Amedeo Avogadro. The currently accepted value is here. Generally, we round Avogadro's number to 6.022 times 10 to the 23rd. Thus, just as 1 dozen oranges contains 12 oranges, 1 mole of hydrogen atoms contains Avogadro's number worth of hydrogen atoms. Figure 3.1 shows samples containing 1 mole each of several common elements. So yeah, if we look here, here's a mole of carbon, a mole of sulfur, iron, copper, and mercury. Okay, the enormity of Avogadro's number is difficult to imagine. For example, spreading Avogadro's number of oranges over the entire surface of Earth would produce a layer 9 miles into space. So not just 9 miles thick, 9 miles into space. Because atoms and molecules are so tiny, we need a huge number to study them in manageable quantities. We have seen that 1 mole of carbon-12 atoms has a mass of exactly 12 grams and contains Avogadro's number of atoms. This mass of carbon-12 is its molar mass, defined as the mass in grams or kilograms of 1 mole of units, such as atoms or molecules, of a substance. So yeah, technically molar mass, it doesn't have to be in terms of grams. It can be in terms of really any mass unit you want. Molar mass is just saying how much mass of whatever you're defining to be an elementary entity, an atom, a molecule, a proton, a car, an egg, how much mass do I need to where once I have that mass, I'm going to have a mole of these elementary entities. So you could put that in any mass unit you want, right? That's the meaning of molar mass. However, this alignment with atomic mass units, to where if you have the mass of an elementary entity in AMU, of any elementary entity, like a vehicle, whatever, in AMU, then that number is also numerically equal to the molar mass. That only applies when you're referring to molar mass in grams per mole. That special alignment between AMU and molar mass is only for the case of grams per mole. But the meaning of molar mass is it's any mass per mole. Right, so note that the molar mass of carbon-12 in grams is numerically equal to its atomic mass in AMU. Same with like sodium, same with phosphorus. Right, the atomic mass in AMU is numerically the same as the molar mass in grams per mole. Right, and so, but where exactly does this come from? Yeah, it comes from the definition of the mole, carbon-12 in the 12 grams, but how does this work out mathematically, and how is this helping us to bridge that gap? So let's keep reading. So knowing the molar mass and Avogadro's number, we can calculate the mass of a single atom in grams. Yeah, so if we have Avogadro's number in the molar mass of any atom, then we can calculate the mass of a single atom in grams, right? Because if we know, for example, if we know that we have, with 12 grams of carbon-12 atoms, and then we know how many atoms are in those 12 grams, we'll just divide 12 grams by Avogadro's number. And so then you're left with, okay, one of those atoms is this many grams, right? But you could do that with any atom or element because we know their molar mass. It's just the atomic weight. Okay, but now it says, we can use the preceding result to determine the relationship between atomic mass units and grams. Because the mass of every carbon-12 atom is exactly 12 AMU, the number of atomic mass units equivalent to 1 gram is, yeah, so we know that, we have Avogadro's number of carbon-12 atoms, right? Well, we know every carbon-12 atom is 12 AMU. Right? So multiply the total number of atoms by 12, and we get the total mass in AMU of this sample of carbon-12 atoms. Well, we know that's equal to 12 grams. So this would be in AMU, and then this is in grams. So there you go. We have a direct relationship between AMU and grams. We can state explicitly a conversion factor from grams to AMU or AMU to grams, right? There's another big piece of that puzzle of bridging that gap. We started off by saying we have no conceptual idea of what an AMU is, but now we do. Here it is. Because we're familiar with what a gram is, right? We can measure grams directly. Well, there you go. There's how many AMU make up a gram. Okay, but now to really clearly illustrate how we use Avogadro's number. So, okay, remember, all of these masses, all of these atomic weights, but not just the atomic weights shown here, even masses of specific isotopes. And really, furthermore, the mass of anything that's in AMU. Any mass, the mass of anything that's in AMU, whether it be an entire molecule, a baseball, a vehicle, right? Because we've got this conversion factor here to go from AMU to grams, and then from grams we can convert to whatever mass unit we want, kilograms, tons, pounds mass, ounces. Right, so we could determine the mass of anything we want in AMU. Okay, so any mass in AMU, remember, by the definition of AMU, that mass is relative to carbon-12. All AMU masses are relative to carbon-12, directly relative to carbon-12. That's the definition of AMU. Okay, and so what you can think about is if we, once again, start with this equation. So you've got Avogadro's number. This is just like a count, right? It's just a number. We have Avogadro's number of something, some elementary entity that we're defining. This could be vehicles. This could be baseballs. This could be protons, whatever. H2O molecules. Okay, well, we know that if all of these entities here, each of them weigh 12 AMU, so we multiply this by 12, and now we've got this in AMU, then macroscopically, this substance here of all of these atoms, or 12 AMU mass particles, is going to weigh 12 grams. So this is AMU. Okay, and 12 is the molar mass of these entities here. Why? Because we have Avogadro's number of these entities, and it weighs in grams 12 grams. So it's 12 grams per mole. Okay, so if we want to get the molar mass of some other substance, some other elementary particles, like vehicles, baseballs, etc., all we need to do is adjust this so it corresponds to the mass of this different particle, right? So if we're looking to get the molar mass of oxygen-16, the oxygen-16 isotope, well, each of those particles is going to have mass 16. So now the total mass in AMU is here, right? Well, whatever all of these particles weighs in grams, all these particles as like an entire substance weighs in grams, that's going to be the molar mass, right? Well, okay, what did we have to multiply 12 times Avogadro's number by to get this? Well, it's just the ratio of the atomic mass of oxygen-16 to that of carbon-12. It's 4/3, 16 divided by 12. So we multiply this by 4/3. Well, okay, to maintain the equality here, let's multiply this by 4/3. Well, look, it's 12 times 4/3, 12 times 4/3. There you go. There's the molar mass of oxygen-16. It matches up with the atomic mass of the oxygen-16 atom. And so there you go. Now you can see clearly why the mass of anything in AMU, if we had a vehicle, right? The mass of a Toyota 4Runner in AMU is going to be just something crazy big. So 5 times 10 to the 20th or something. Well, okay, what did we multiply 12 by to get 5 times 10 to the 20th? We'll just multiply that on this side as well, and what are you going to get? 5 times 10 to the 20th, because this is 12 as well. There's the molar mass of the Toyota 4Runner. So it's because of the way that the AMU is defined, with the 12 AMU for carbon-12, and the way that the mole is defined, the 12 grams of carbon-12, what that results in is all we're doing with the mole, with Avogadro's number, is purely scaling up atomic masses. That's all we're doing. So I'll say it again. If you find the mass of anything that you specify to be an elementary entity, a baseball, a proton, a neutron, a H2O molecule, a big hydrocarbon, whatever you say is an elementary entity, and you get the mass of that entity either by, you could weigh it on a scale, or if it's atomic sized, you could go atom by atom and add up the atomic weights of all the different atoms. Okay, if you get the mass of that elementary entity in atomic mass units, in AMU, then that number, that quantity, is also the molar mass of that elementary entity in grams per mole. Meaning that many grams, you need to accumulate that many grams of that elementary entity, and once you have that many grams, then you're going to have a mole of those elementary entities grouped together. Okay, so now with that in mind, We've up to this point, we've really only focused on atomic masses, the masses of atoms, single atoms at a time. So now let's branch off from atoms and think about the other atomic-sized fundamental particles that we talked about in chapter 2, which were, so any substance, any given substance, you can categorize as either it's just atomic, just composed of single atoms, like the noble gases, for example, or you could have molecular substances, or you could have substances to where in the solid state they form lattice structures. You can identify that they're not molecular. You can't identify a distinct molecule, but they're also not just distinct atoms either, like noble gases. Okay, so starting with molecules, when we're thinking about masses of molecules, what we have is molecular mass or molecular weight. And all you're doing in this case is you're going to add up the atomic masses, the atomic weights of all of the different atoms in each molecule to get the total mass or weight of the molecule, right? So if we know the atomic masses of the component atoms, we can calculate the mass of a molecule. The molecular mass or molecular weight is the sum of the atomic masses in AMU in the molecule. For example, the molecular mass of H2O is you take 2 times the molecular weight of a single hydrogen atom and add that to 1 times the molecular weight of a single oxygen atom, and there's the weight of an H2O molecule. Now, remember, you used the molecular weight here of hydrogen and oxygen, or the atomic weight, because in general you have like an H2O as a substance in nature. It's that mixture of the isotopes. If you had a special case where you knew you had a water molecule that had 2 hydrogen atoms that were the mass number 1 and an oxygen atom that was this mass number, well then, yeah, calculate that specific molecular weight. But in general, with natural substances, we're going to be using the atomic weights here, these average atomic weights of all the isotopes. Okay, and so 18.02 AMU is the molecular weight of water. So now what would be the molar mass of H2O? Well, this is AMU. It's 18.02, which means you need to accumulate 18.02 grams of water, which you could actually do that, right? You could measure out 18.02 grams of water in a beaker. Well, then that sample of water has a mole worth of water molecules in it. There's 6.022 times 10 to the 23rd water molecules in that beaker. Okay, so now to go back to the thought exercise of thinking about like a vehicle in terms of moles, you might be thinking, well, man, how do you calculate the mass of a vehicle in AMU? I mean, how are you going to add up all of the different atoms contained within the vehicle, all of the carbons and the irons and everything? Well, no, in that case, the mass of the entire vehicle is so much larger than the mass of like a single atom. You're just going to put the vehicle on a big scale and get its mass in tons, convert that to AMU, and there's the molar mass, which is, again, it's like insanely ridiculous to think about that. You would need that many grams of your vehicle. I mean, you could put that in something like megatons. Once you have that many megatons of your vehicle, then you know you have 6.022 times 10 to the 23rd Toyota 4Runners, right? That's completely ridiculous, but I mean, no, you could do those calculations. In this case, in the case of a water molecule, we can't put a water molecule on a scale. No, we're at that atomic size scale, which is really when we're going to be using AMU. So no, in that case, we're going to go atom by atom. Okay? So from the molecular mass, we can determine the molar mass of a molecule or compound. The molar mass of a compound in grams is numerically equal to its molecular mass in AMU. For example, the molecular mass of water is 18.02 AMU, so its molar mass is 18.02 grams. Note that 1 mole of water weighs 18.02 grams and contains Avogadro's number worth of water molecules, just as 1 mole of elemental carbon contains Avogadro's number worth of carbon atoms. Exactly. Okay. Now, finally, note that for ionic compounds like sodium chloride and magnesium oxide that do not contain discrete molecular units, we use the term formula mass instead. The formula unit of NaCl consists of one Na plus ion and one Cl minus ion. Thus, the formula mass of NaCl is the mass of one formula unit. So, okay, what they're trying to point out here is that, so we've got atomic masses of associated with atoms, but there's other atomic sized particles, right? We have molecules. So we're not going to call the mass of molecules atomic mass or atomic weight. No, we need to change the name. It's going to be a molecular mass or a molecular weight. All right, but when you're looking at a substance, it's either going to be an atomic substance like a noble gas. It could be a molecular substance, or it's going to be that lattice type substance. Well, we can't call a lattice type substance like a metal or an ionic compound. We can't call that a molecular mass, right? Like something like NaCl or magnesium oxide. So we call that a formula mass or a formula weight, right? The substances to where the chemical formulas are going to have to be the empirical formula. You can't write something like Na2Cl2. That doesn't make sense. So when we're calculating that, the mass at the atomic scale of a substance it's not a molecular substance, but it's also not a distinct atom type substance like a noble gas. It's a substance that you can only represent with an empirical formula. Then we calculate that atomic level mass by summing the masses of the atoms in the empirical formula, and we call that the formula mass or the formula weight. So for sodium chloride, you take the mass of a sodium atom and add that to the mass of a chlorine atom, and there's the formula mass of sodium chloride. Now you might be saying, well, wait a minute. No, we should have taken the mass of a sodium cation and added that to the mass of a chloride anion. And, well, first of all, the only difference between the sodium cation and a neutral sodium atom is a single electron, which is pretty much negligible. Same with the chloride anion. But even so, that electron didn't disappear, right? Here we didn't get some new outside electron. As a unit, that electron didn't go anywhere, right? So this is actually still the exact precise formula mass anyway, even though we did use the actual atomic weight of sodium and chlorine instead of the ion weight. Okay, but now here's the formula weight of sodium chloride in AMU, which means the molar mass is going to be 58.44 grams per mole. So what do these mean in the context of a crystal-like structure? Well, okay, a sodium cation and a chlorine anion bonded together as a pair, that's the most fundamental unit of the sodium chloride substance, right? And there's its mass. Okay, and so now, but the molar mass is just saying I would need 58.44 grams of these sodium cation, chloride anion pairs. I would need to accumulate 58.44 grams of those pairs. And once I have that, then I know I have a mole of those pairs.